Hi there, in this lesson we're going to be looking at multiplying rational expressions. And really, again, rational expressions are just expressions that are written as fractions. So if we consider these first two examples, when I look at something like this guy, there's two ways that I can approach multiplying these fractions. I could multiply straight across and get a 28 over, let's see, the 12 times the 14. And you'll see right away why this makes this a little bit difficult. 168. And then from here, I have to reduce this thing. And when we look at a 28 over a 168, it might be pretty tough to identify what divides evenly into each. Okay, we might start off taking a guess. Maybe we'll guess something like, I don't know, a 4. Okay, and we'll find out that this reduces to 7 over the 42, and then we can probably see that the 7 over 42 reduces to a 1 over 6. All right, and that's fine. You can do it that way. But remember, there's something else we can do. Whenever we're multiplying fractions, we can always cross-reduce. In other words, we can reduce each of these fractions individually, but we can also look at the numerator here and the denominator here. Okay, and so like the 12 and the 4 can reduce to a 1 and a 3. The 7 and the 14 can reduce to a 1 and a 2. And so when we look at this, it makes it a lot easier now. I've multiplied numerator times the numerator. 1 times 1 is a 1. 2 times 3 is a 6. So I get to the 1/6 much faster by reducing everything that I can first. All right. And keep in mind that you could reduce each fraction individually first as well if you wanted. Like here, I could reduce this to a 2 and a 7, and then I can cross-reduce the 2, and this guy is a 6 and a 1, and then a 1 and a 1. But you see, I get the same thing either way. So remember, anything in a numerator reduces with anything in the denominator when we're talking about multiplication. And it's the same thing with the next one. Again, I can reduce each fraction individually if they reduce. In this case, they don't. So I can reduce any numerator with any denominator. The 9 and the 27 reduce to a 1 and a 3. The 25 and the 10 reduce to, let's see, a 5 and a 2. And now I can multiply straight across. It gives me a 5 over a 6. That's a lot easier than multiplying straight across and then reducing. So keep that in mind. When we multiply fractions, we can always cross-reduce. And it's going to be the same thing here, because multiplying rational expressions is just like multiplying fractions. We're going to factor each polynomial completely. So we're going to get all our factors out in the open. And then we're going to reduce. We're going to reduce each fraction individually. We're going to cross-reduce. And then we're going to multiply straight across. And in this step, when you multiply straight across, you can leave that in factored form. Okay, so we don't actually have to multiply it out. We're just going to leave it in factored form for now. And go from there. All right, and for our domain restrictions, we're not going to be looking for those right now. We did a lot with domain restrictions, but just to speed up this process and get us used to multiplying, we're going to forgo the domain restrictions in these particular examples. Okay, so that's your disclaimer for those. So if I look at this first one again, I want to factor everything completely. So like an x plus 5, I can't do anything with. I'm going to leave it as an x plus 5. Underneath here, the 7x minus 21, I can factor a 7 out, which leaves me with an x minus 3. Over here, the 14x, I can't really do anything with. It's a 14 times an x that's already in factored form. And then down here, this denominator, if you need to, take it off to the side. Okay, there's nothing wrong with taking this off to the side and showing your work, building the bridge, coming up with the 5 and the -2, and then factoring it using your shortcut. Okay, some of you are going to prefer taking that off to the side and doing your factors individually, and then coming back and writing these in terms of expressions, rational expressions. Okay, but yeah, feel free to take some work off to the side. Now I reduce. I look at each fraction individually. Nothing happens. So then I cross-reduce. The x plus 5s cancel out. Remember, anything in a numerator with anything in a denominator. The 14 and the 7 can reduce to a 1 and a 2. So now when I look at what I have, again here, this became a 1 because that's what happens when you cancel things out through division. And now I multiply straight across. I have 1 times a 2x, which is a 2x. In the denominator, I have an x minus 3 times an x minus 2. And I'm just going to leave it like that. Okay, I'm going to leave it in its factored form, because typically we're going to be finding domain restrictions and that kind of stuff anyway. So leave it in factored form. I get the 2x over the x minus 3, x minus 2. And that's it. If I look at the next one, just like when I'm dealing with regular numbers, if I have a whole number, I can write it as a fraction by just putting it over 1. So I'm going to put this guy over 1. And I'm going to factor everything completely. If I look at the 2m plus 5, I can't factor anything out of there, so I'm just going to leave it the way it is. The denominator, the 3m minus 6, I can factor a 3 out. Leaves me with an m minus 2. Over here, I can build a bridge and factor this one. It's going to be an m plus 3 and an m minus 2. And now I look for any common factors that I can cancel out. I see the m minus 2's are common, so I can cancel those out. Nothing else cancels out, so I'm going to write this in its factored form. I've got in my numerator the 2m plus 5 times the m plus 3. In the denominator, I just have the 3 left, and that's it. I'm going to leave it in this factored form. Nothing else canceled out, so that's my answer. If I look at the next one, again, a 3x squared I can't really do anything with. If you want to think of it this way as a 3x times x in terms of multiplication, in terms of all 3 of those individual factors you can. Over here, the x squared minus 4, that is a difference of squares, so I'm going to factor that into an x plus 2 and an x minus 2. The denominator has a greatest common factor of x. So I take the x out, that leaves me with an x plus 3. And here's why I showed that 3x squared as the individual x's, because now I can see that one of these x's is going to cancel out with the one that's in the denominator. I've got a pair of x plus 2's that can cancel out. And so now in my numerator, I've got a 3x times an x minus 2. In the denominator, I just have the x plus 3 left. And that's it. I leave it in that factored form. Okay? Just keep going with these to give us a little bit more practice. If I put this over 1, again, I'm factoring this thing completely. Here I can factor a 2 out. Here I can factor a 2 out, which leaves me with an x, a 2x minus 3. Over here, this numerator, you're going to have to build a bridge, and this is one you'd probably want to take off to the side because you're going to have to factor by grouping. So again, based on the difficulty of the factoring, take it off to the side. I build a bridge, that's a 36. It looks like a -9 and a -4. For your purposes, you're going to split up the middle term and do some factoring by grouping. When you do that, you should come up with, let's see, a 3x minus 2 and a 2x minus 3 for your 2 factors. All right? And so this factors into the 3x minus 2 and the 2x minus 3. And now I cancel out any common factors that I might have. In this case, the 2's cancel, the 2x minus 3's cancel. And so when I look across at this denominator, I've got 1 times 1. I essentially don't have a denominator anymore. I don't want to leave this thing over 1. So all I'm left with is the x minus 7 times the 3x minus 2. All right? And I could put that over 1, but when I divide by 1, it just gives me this thing, so I don't write it as a fraction anymore. Okay? Same thing with the next one. This guy's going to factor into a b plus 2 and a b plus 2. That's actually a perfect square trinomial. I could write that as a b plus 2 squared, but I'm going to leave it split up because it's easier to see canceling with my factors. Here with this one, I can factor out a 2, which is going to leave me with a b squared minus 4. Up here, I can factor out a 5, which leaves me with a b minus 2. Down here, I have the 4b. And now from here, it doesn't look like anything cancels, but that's because this guy's not factored completely yet. Remember, a b squared minus 4, that's a difference of squares. It factors into a b plus 2 and a b minus 2. So I'm actually going to go back here and replace this thing to make sure this thing is factored completely. And that's the other advantage of taking things off to the side and factoring them, is I might not have to rewrite this entire fraction so many times. But now, I can cancel out some common factors, the x plus 2's, and just one pair of the x plus 2's cancels. Notice I have 2 in the numerator, 1 in the denominator, only 1 second cancel. The b minus 2's cancel. And it looks like that's about it. In my numerator, I've got a 5 times a b plus 2. In the denominator, I have a 2 times a 4b, and I'm not actually going to leave that as 2 times 4b. I suppose I could. I'm just going to write it as 8b. And that's it. In this one, the numerator, I can factor out a 2, which leaves me with a 2x plus 3. In the denominator, that's going to factor into an x plus 4 and an x minus 3. Again, feel free to be taking some of these things off to the side. Over here, this numerator is a difference of squares, an x plus 3 and an x minus 3. The denominator, you might have to build a bridge and come up with, again, this one is when we take off to the side. So you might build a bridge. You come up with a 6. Two numbers are going to be the 2 and the 3. You're going to have to split up that middle term and factor by grouping. When you do that, you should arrive at a 2x plus 3 and an x plus 1 for your two factors. And now from here, we're going to cancel out any common factors. So the 2x plus 3's cancel out. And I look around, and that's it. You know, that's the, oh no, the x minus 3's also cancel out. And that's it, okay? So now everything's canceled. So I've got a 2 and an x plus 3 in my numerator. In the denominator, I've got an x plus 4 and an x plus 1. Okay? Last one here. Again, I want to factor it completely. This numerator is already factored as a 4 times an x. This denominator, again, take it off to the side if you need to. You do the 3x squared minus 7x plus 4. Trying to do factoring by grouping within the confines of that problem is going to be very difficult. Okay, so take it off to the side. Do your factoring by grouping. Split up that middle term, factor by grouping. You should come up with a 3x minus 4 and then x minus 1. And again, I expect that you already know how to do that, so I'm not showing all the steps in between. Should be something we're very good at by now. This one, again, I would take this guy off to the side. Right away, I see a greatest common factor of 2. So you might factor the 2 out, which is going to leave you with an x squared minus 10x plus 21. And now I can use my shortcut for what's inside there. It's going to factor into an x minus 7 and an x minus 3. So I come back over here, and I put that in its spot. So we can take those things off to the side. The more complicated it looks in terms of factoring, the more often you should take it off to the side, do your factoring, and then come back to your fractions. In the denominator here, I can factor out a 4x, which leaves me with a 3x plus 2. And now I cancel out any common factors. In this case, the 4x and the 4x cancel. And really, that's it. That's the only thing I see that cancels out here. So when I multiply straight across the numerator, I've got the 2, the x minus 7, and the x minus 3. Again, I'm leaving this in factored form to make it really easy on myself. Down here, I've got the 3x minus 4. I've got the x minus 1. And I've got the 3x plus 2. And it's okay that more didn't cancel. Sometimes that's just the way it goes. Factor everything completely. Cancel out any greatest common factors in numerator and denominator. And then write your answer in factored form. Okay?